Is this on? Welcome to this talk on practical Lambda Calculus. I don't think the Lambda Calculus needs a lot of introduction after Philip Wadler's keynote yesterday, so we'll skip the theory and go right to sort of the practical stuff, the things that you... What?
Yeah, so I'm not sure if we're on that track or not.
Right, yes.
But I think that was one of the tracks, and no one told us which track we were on. So we're probably in the finance and banking track.
Yeah, we're on some track. Practical things. So you need sort of an environment to work with the Lambda Calculus. That's sort of been missing for a long time. So luckily, Jonas has sort of rectified that.
So yeah, keep making new environments. So we have an eBank setup, which runs a standard ML program that runs a Lambda Calculus interpreter. And when it outputs meep, 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 that means it's running. So now we have kind of a Lambda REPL, so we can do like call Lambda functions, and we can get the result on the next line.
Right, so maybe we should talk about the rules and what we have to work with.
Well, we kind of went through the rules yesterday at Philip's talk. There are three constructs. We have variables, and we have Lambda abstractions, and we have function applications.
Right.
And we have sort of one computation rule or evaluation rule, which means that if you have some Lambda and you apply it to a value, you do the function application thing, you take the body of the Lambda, and you replace every occurrence of the parameter with this argument.
Right.
So we have like a really useful example here. We can step through this. See, this should. So this is a function that takes an argument A and returns the remaining this body. So when we evaluate this, like one step, we should replace all the A's with foo.
Right.
And now we have a new function that takes a B, and this is the next argument, and we can evaluate this, and we replaced all the no B's in the body with bar, and we can do the next step and replace the C's with quarks.
Right, so this is very nice, but it's not entirely clear to me how this is like, how do you do practical things with this? Say you're running some business in the Omniverse and you want to do some computation, maybe you want to count things like revenue or something. How would you go about doing the more practical stuff? Like,
so as we've kind of learned, in the Omniverse, we always have these lambdas.
Right.
We might use different symbols for them and stuff.
Yep.
I'm not sure if you have numbers everywhere, but if we start with this, I'm sure we can like make numbers.
Okay, so you make numbers. How do you make numbers? Because
so like one of the things we could do with these lambdas was we could do function application. So we kind of, if you do that over and over a number of times, so if you do like a lot of function application,
right.
That sort of appears to be kind of the most basic thing you can do over and over.
Sure, yes.
So if you do function application 4 times, we want that to be the number 4.
So that's basically just your interpretation, right? So, so you're saying now if you have this, you're going to think about that as being 4?
Yes, I think we can decide that this is number 4. So we do this, and we define the number 4.
Okay. So just to be clear, the party hat equals is not part of the Lambda Calculus, right?
Yes, that's kind of the macro system we built on top.
Right.
Which means that whenever I write 4 now, I can do this replacement and get back the definition I decided on.
Right. So it's for convenience, or because you're lazy and don't want to type Fs.
Yeah.
Mm-hmm. Good.
So if
what's the smiley face?
So that's kind of the omniversal symbol for meaning that no, this symbol is defined.
Right. So if you have a mouth and 2 eyes, then that's the.
Yeah.
Okay. Good.
So Yeah, so what we said was 4 is a function that takes 2 arguments and applies the first argument 4 times to the second one. So 0, which is sometimes better to start with than 4, should apply the first argument f 0 times to x.
Right.
So it just returns the second argument.
Right. This is still sort of a game of you're pretending, right? In some sense.
In some sense.
That this is the number 0, because all it really is that a function.
Yeah, but I don't think it would be like happy if it was just for pretend.
Oh, okay, good. So, but now we have numbers. It seems you have to sort of manually construct them.
Yeah, so this gets tedious after a while. So writing a bunch of f's.
Right.
And so on.
So sort of the first function we want to write on numbers that takes a number as an argument is probably to
add something to a number.
Right.
So we'll make like a successor function.
Which is like a factory to create numbers or something?
Yeah, so it's, and I think that's like from the Gang of 4 book, number creation factory.
Right. Yes. Good.
And it should take a number as an argument and return a number that is 1 higher.
Right, sure.
So we're going to build a new number the same way we did before. And I don't really like doing this correctly on the first try, so we're going to do this first. See that.
It looks happy, so it's probably correct.
So this should
get us the successor of 0. You see, this takes 3 arguments, applies the third to the application of the second to the first.
Yes, absolutely clear, yes. But that just gave you 0.
Yeah.
That's just 0, so that didn't do anything.
Yeah, but at this point it's like off by 3, which isn't too bad.
So could you apply the 3 f's?
Yeah, so if we make this add an additional f to the result of that, so we saw that
Right, yes.
s gave us 0 back, but if we add an extra f, we should get 1 more f's.
Right, okay.
Now it's twice as happy. And we get 3 f's.
2, 3 f's, excellent.
Yeah. So
okay,
this is, it's not obvious that this is less tedious than writing a lot of f's.
Now, maybe you prefer s.
But you get like several lines of computation before you get to the f's.
Sure.
Which I think is good.
I don't know how many f's we have.
But could you like generalize this to do more like addition?
Yes, now we have like
we have 0 and 4 and 5.
Yes.
Which are pretty good numbers.
We could make 9, I think.
Yeah, so if we want to like make 9 with them,
we could add more f's to 5.
Sure.
But yeah, we could try to make like an addition function.
Sounds useful.
So we do like plus, and it should take, so we say it takes 2 arguments.
Right.
By that we mean that it takes 1 argument and returns a function that takes the next argument.
And we have 2 numbers, and kind of the only thing you can do with a number is
apply it.
This is kind of strange to me because now you're saying you're using the thing you call the number as a function.
Yeah.
Yes, okay. This is...
So the number should look kind of like this. It should take an f and have a bunch of f's in it. So we're kind of thinking, well, what can we replace the f's with in order to make an even larger number?
Okay, well...
Which is kind of like replacing the successors when we...
Okay.
Like, we should have as many f's as we started with s's here.
Right. So,
we're going to replace them with s's.
You're going to replace the s's with s's?
Yeah, I shouldn't.
That's okay. That
should make
useful.
a really large number.
Yeah,
but we can also replace this x on the end, which is like what corresponds to the 0.
Right. So that's you will sort of like plug in the other number.
Yeah. So if we add b
so
into
you put
this
the other number in here, and then it's just continue with some extra f's.
Yeah. So we add sort of all the f's from a onto the number b, or the f's from the number b. I don't know.
Okay, great.
We can see what happens.
Sounds very nice in practice or in theory. But.
So it turns into this thing,
and it should evaluate into.
Right. So is that 1, 2, 3, 4, 5, 6, 7, 8, 9 f's? Okay, excellent.
And we at that point we can get to like 10 pretty easily, which is...
I think that's one of the more common numbers.
10 sounds useful.
Yes,
Could
no,
you make like 100
And I'm
now?
sure we can get like 12 or 15 or something this way pretty easily. But if you want to go like really large, like up to 100.
100 is huge.
Yeah. I'm not sure addition goes that far.
No, but
so
you can generalize addition, right? In some sense.
To multiplication, which is kind of like super addition, I think.
Yes.
And we have...
Which also takes 2 arguments.
Which those are the numbers. With what would you replace?
So we want to replace the f's with something.
Right.
And the x is kind of easy because the x is what we want to replace the number 0 with. And I think that when you multiply something by 0, you get 0 back, so that one should be pretty easy.
Right.
So at this point, it's like assuming that, well, if we have the number 1, we should add, if a is 1 and b is like 8, we should add 8 to it.
So you can like add 8.
Right.
It should work pretty good for multiplication
So
by 8.
this again is now just you sort of cheating with your macro system, right? So
Yeah, so you can pretend that this is like a bunch of lambdas if that's
yes,
easy to
and
read.
we can see them sort of expanded as the first step there.
Yeah. So you can, you can do like, do like this and get the expansion like so. Yeah, we don't have 8, so that's
No, we
probably
don't have
a
8
bad
yet.
number to start
Right.
with.
So you should use like 9 or 10.
Yeah, and I think that kind of no matter which number we use,
Right.
sort of in general for multiplication it could be any number.
You think it should not just work for 8?
It's a good start. But if you plug in b instead,
Right, yes.
we should add b sort of a times 2, 0.
Right, yes. Okay,
So
let's see if it works.
this way we should get to
100, which I think is the largest natural number.
Right. Is this 100 now?
Just to be clear, so we did like some late night optimization of this yesterday.
Yes, so it's now blazingly fast.
It used to be slow.
Yes.
So I'm not sure. This is kind of where.
Do you know Emacs, so maybe you can count the Fs, so I don't have to?
So I don't know Emacs, and I
kind of Googled this yesterday. And I Googled the wrong thing and got like a really Emacs answer, which was like, you have to use all your fingers. But then I remembered that, I wanted to count, not search within a region or something.
Oh, okay.
And it was quite simple.
Right.
So
100
we got
Fs.
100
Great.
occurrences of F.
I think you should hold on to 100 in case we need it later.
Yeah, so hopefully we're not going to need it because it's like
Way too large.
Yes. So now we can add things. What about like if by some ill chance you would lose money? Maybe you need to
So I think that in economy you only need like things that make numbers go larger.
Okay.
But like if you're not using this for finance and banking, you might want to.
Sometimes things go down.
Yeah. So at that point we want to like do subtraction and a predecessor function.
Right. That should be fairly easy, right? So all you need to sort of first you could get rid of one.
Yes, I'm
F.
sure you could code it in Emacs pretty easily. Like
Yes.
you take this string and remove like an F and a couple of parentheses.
Yes.
So that's like the easiest way to do it. But then we're kind of back to the thing where it's kind of hard to imagine that you don't have Emacs someplace in the omniverse.
You probably do. So.
But I think that's like not proven true or false, whereas you will always have the Lambda Calculus. That's like now.
Mm-hmm.
So we can do.
So
we want to do a predecessor function.
Right.
And it's kind of so.
It's less obvious what you want to replace the f's with in a predecessor function.
Yeah, you want to replace it with something that kills one F and then keeps all the others.
Yeah. Or you want to replace like most of the f's with something or something else.
Right.
And then we're back to the, well, that's easier to do in Emacs.
Yes, and not so easy. with just the function.
So there's like a couple of ways to do the predecessor, at least. We're going to do the one that I think is the easy one.
Right.
So I have the idea of counting in pairs.
Okay.
Which, I'll just read it from the side. So like the pair of 0, 0, you can start with.
Okay.
And you can count up in the first part of the pair.
Right.
And move the old value for the first part of the pair into the second part. So you can move this 0 into here, and you move this 1 into here at every step. And then if you count it to 3, you should have 2 as the second.
Right, and that would be sort of the predecessor to 3. You could just sort of, because you let the smaller number piggyback on the number you're counting up to, right?
So if you kind of do that, like n times for the number n, and pick the second number, you should get a number that is 1 smaller.
Okay, great.
Which is like...
But now we need like data structures, right? Because
so in order to count in pairs, we need pairs.
Right.
So we're going to make...
Pairs like obviously a function that takes two arguments.
Right.
It's going to return something, and it's probably going to return a function.
Right.
Since that's
it usually does.
So it's going to return a function that takes 1 argument.
And that argument has to be a function.
Now there's a lot of functions.
It's kind of, it's not like super hard to guess that this has to be a function.
Right, no.
Since that's everything we've got.
Yeah, so.
I'm not sure like how much timing is. Yeah, it's probably a function.
Right.
And the only thing we can do with the function is apply it, so we're going to apply it to the 2 arguments.
Right.
So that should work out somehow.
So how does it work in practice if you use it for something?
So we can
make a pair of foo and bar.
Right.
And then we get a function that takes an argument f and applies f to foo and bar.
Right. And how is this a pair now?
So we should be able to pick out... So this is a function that should take 2 arguments.
Right.
Foo and bar. If we apply this to a function that takes 2 arguments and return the first one, we should get...
Oh, you got the first one, right?
Yeah.
So we can turn that into a function that takes a pair and applies it to a function that returns the first argument.
Still foreign to me that you would sort of apply the pair to something, but that's good.
Yes. So we take the first, we should get back
right.
foo.
And you can do similar thing for second, I imagine.
Yeah, you get...
Where you would return b, right?
Yeah, so it takes a pair, applies.
It's kind of interesting that like the lambdas were not the craziest character you saw.
So we take a function of 2 arguments that returns the second one, I think.
Great.
So in the pair foo and bar, and we take the second of it.
Looks like this, and we get bar back.
Okay, excellent. And now you can make a predecessor function, right?
Yeah, so now we will start by making a function that we're going to replace all the f's with.
Right.
We'll use like a helper function for that.
Right.
So it takes a pair.
This is the counter.
Yeah, so this is the thing that
dies. Yes. Yes.
The function that should take this and return this, and
right,
take
sure.
this and return this, and
Yes.
so on. So it takes a pair that looks like that. It should make a new pair and take the successor of the first part of the pair.
And then just the first
take
part, right?
the old first part of the pair
Yes.
into the second part of the pair.
And it's happy.
Yeah. So if we start with the pair 0, 0,
you should get 1, 0. And that's 1f and 0f, so yes, we're good.
Yeah. I lost my stuff.
you can see that it works for larger numbers. Let's see.
I think we did 3
Right.
calls of the helper function.
Right.
And we got...
And now you could pick out 2 if you wanted to, right?
Yeah.
That's sort of what you're aiming for.
Yep. So now we can make the predecessor function using that
helper function.
Right. So pred should be a function that takes a number, calls the number, replacing all the f's with pred help, and starts with the pair 0, 0.
Right.
Replaces the ending 0 with
right.
a pair.
And you need to pick out the second one, right? Yes.
And that's happy too.
Right. Could you do the predecessor of like 10? We have 10, right?
You want to count
This is probably 9 Fs. 1, 2, 3, 4, 5, 6, 7, 8. 9 Fs, excellent.
Yeah. So,
could you
do we
do
have 2? No.
Oh, you're making like crazy large numbers.
Yeah, so I think like predecessor works for, I think it works for 40.
Yes.
I'm not sure it works for 100.
Right.
It's like super large.
It needs to count up to 100 again, and I have to wait for it.
It's not entirely clear that it would terminate.
We can check to see the...
This should now be 40 Fs. Yes.
40, so this is the number 40. And we can take the predecessor of 40.
It kind of counts back to 40.
Right.
And then throws 40 away.
Yes. And then you have 39. So I imagine doing this...
It's nice that you can follow along as it computes. You can spot mistakes kind of during.
Yes.
Instead of having to
So you
go
can
back.
terminate in case it's calculating wrong.
Yeah. I have like a keyboard code where I can kill the process if I see that something's
done?
correct.
But
Great, and this should be now 39 Fs. So maybe we won't do too much subtraction because you'd have to do this over and over again, right? So if you wanted to subtract 2 from 40, you would count up to 40 and then you would count up to 39.
Yeah, so we can like really quickly do
Do the subtraction function.
which means that we want to take the predecessor of A B times.
Right, this is now very similar to the addition.
Yeah.
Right.
So we still don't have like 2, do we? We have 4 and we have 10.
Yeah. This should now be
You can get
hopefully
like
6
6.
Fs, which is a new number to us, so it's useful in that sense.
Yeah, it's one to hold on to. We might need it later.
Yeah.
I don't want to
Do
do
like
great.
this every time.
No. So you're sort of caching the
So
results.
it's 1, 2, 3, 4, 5, 6.
Yes. Oh.
Yeah. So clearly we can do stuff with numbers.
Right. Maybe we heard earlier that you can do more in programming than just arithmetic, I think.
Yes, there was some point made about that you could use like symbolic logic for things other than numbers.
Yes.
So we kind of touched on that because we needed pairs in order to do stuff in numbers.
Right. But maybe like having an arbitrarily large list of things. Would
Yes,
be
a sort of.
right.
So the number is kind of the simplest recursive data structure. It's defined in terms of themselves. It can be 0, a successor of a number.
Right. It sounds
making
almost like a
lists
list.
should be kind of similar.
Right.
Uh,
But you also need things inside
So
the list, right?
we have like slides and things. So
Right.
numbers look like this.
but
It's
not
structurally
because
very
we have
similar.
Really, really large assets
Right.
in them.
Yes.
And lists look like this. So they're the same, apart from the
have
stuff the list contains.
Yes, you have some things. Sometimes you're interested in the contents of the list, though.
At times.
Yes.
So we have this kind of illustration that
Right. So numbers are lists without the junk in them.
Basically
Yes.
lists.
Right.
I think it's easier to use a list in place of a number than a number in place of a list.
Yes. So you could sort of simulate numbers using just lists now, right? If you didn't care about the junk that was in
If
the
you only
list.
cared about the length, it would be
Right.
kind of like a number, since
Yes.
the
So-
length of a list is a number. Yeah.
Right, and it's all make-believe anyway, so.
So let's see. I'll just see all the nice and useful stuff we made so far.
Right.
Let's see.
So we have like zero and successor, looking
Right.
like that, and we want to have cons and nil for lists. So
Right,
nil is
sure,
the empty
yes.
list.
Should look a lot like 0.
That is 0.
We're going to use different.
Variable
I mean,
names, but other than that, it is the function 0.
It's the same thing because the variable names don't matter, right?
Yeah.
It's just for convenience.
So, and cons should.
Look a lot like successor. But
Right.
successor just takes the number that it is more than, whereas a list should
Right.
take the list that it is
Mhm.
more than, and
some
an element that it
Right,
adds
yes.
to the
Mhm.
Beginning of the list. So should take
an element, a new head.
Right.
and sort of the tail of the list, and then we'll make a new list.
On the form of the same way we made the nil thing.
Right.
And we'll. So if we do,
So where would you put the?
we'll do this one incorrectly as well. So we cons foo onto nil,
Oh, this is just going to be the same thing
and
you
we
started
get
with.
Nil back.
Right. So you
So we
forgot
want
to.
do an additional cons
Right.
somewhere here.
if we cons the head onto this expression, it's
Right.
again twice as happy.
Yes. And now you
Uh,
have a foo inside.
Yeah.
So now we can make like
Now you can do that multiple times. So-
cons foo, cons bar, cons x, nil, and get this thing.
Yes. So now it has all the things, and then it also looks very similar to the numbers.
Yes, now you can see that instead of f's there are
C's,
Right.
and each C has an additional element.
Right.
But it's a function that kind of holds on to all the elements we put into
Right.
it.
So you said that this is a list.
Yep.
Yeah, we probably have time for stuff. So now we have lists
Looking like this.
Right.
Cons do now.
How
And
would
numbers looking like this. And
We should be able to apply them in order to replace the conses with something and
Right.
the nil with something.
What would be
Same.
the result of sort of replacing the conses with s and the nil with 0?
I don't think we have like
Like 1 or 2 yet, so it wouldn't
Oh, yeah.
like evaluate much.
Right.
But yeah, you should be able to replace the cons with plus and the nil with 0 to get the sum of a list.
Okay.
But this kind of replacing cons with something and replacing the empty list with something turns out to be the sort of right folding a list,
Right.
which suggests that replacing successors and 0 in that way is the right fold of a number.
Okay.
Which we have like, there's a number of quotes on this, and I'm sure that if you go like a type theory direction, you'll often find something along these lines at the elimination form,
Right.
elimination rule for a type. But like smart people have said that folds are kind of important, so it can
Right.
make sense that things ends up being folds. So
Right.
Oleg said this in an article related to something entirely different.
Okay.
That you can basically build everything if you have fold right.
Right. So
So some examples.
so now you
I
could
think
do
it's-
some if the things you have in your list are numbers. Is that true?
Yeah, so we can do like cons successor of 0 onto cons successor of 0 onto nil.
Right.
And we should be able to fold this the same way, like so.
Right, so now you're replacing the conses with the plus and the nil with the 0, right?
Yeah. So
Okay.
it should add those two numbers together.
So this is the fault right for it.
Yeah.
And this gave us 3, and you had 1 and 2, is that correct?
Hopefully we had 1 and 2.
Right, okay.
Not going to check.
No, good.
And we can skip a slide.
I have no idea what it says.
Right,
So a fault for numbers would look like this, which is what we've been doing so far.
right.
Uh,
So, but you could do the same sort of replacement, or we have been doing the same kind of replacement for numbers, right?
Yeah, so we have this, we have like a really good example. Did we store this one? Yeah, so we have a list, and we
Right.
can get like the length of it
Yep.
by replacing all the conses with a function that takes 2 arguments.
It's going to ignore all the elements because it's just counting how many elements.
Right.
And it can take the successor of,
The second element. The second element
Right.
should be.
Oh, it's you miss a lambda, right?
I'm missing a lambda.
I haven't made any mistakes so far, and we
Oh,
we
okay.
made last-minute changes to make like a really awesome error message based on the talk yesterday.
Right.
So
Yes.
we're going to leave it in for now.
Okay. I was kind of counting on making a mistake.
Yeah, it's kind of disappointing that you
usually
haven't.
works out. But it should take the successor of the n
Mm-hmm.
and replace the empty list with 0.
Right. And this should now give you the, oh,
Yeah, so
This
that's
tells us that
unfortunate.
there's missing a lambda.
Yeah, it was wrong.
If we remove it, if we add it in,
we should get this again. And we can probably remove the picture.
And now we have the length of the list.
yeah, so it's 3 long.
Right. So how about taking the length of a number? Could you do that? Because
So if
it's-
you have like the number, we have the number 4, right?
yeah. So you could replace the s's with s's, I guess, and the 0 with 0.
Yeah, so that's it. So according to this, so
The
Oh, it
number
gives you
4
4,
is-
right, yes.
The length of 4 is 4.
Yes. And this is one of the things that I kind of like about these numbers is that it's very tangible how big a number is. You can sort of measure it, right?
Yeah, so you can measure. Yeah, so like the same way you can like say, well, we got a fish that was this large.
Yes.
You can also say you got this many fish.
Yes.
Because
this
the only
many
number
fish,
that
right.
is that
Yes.
large is the one with that many f's.
And it's fairly obvious that, say, like 8 is larger than, say, 4, right? Because it's just longer.
yeah,
Yeah.
I think we even have 8. No, we don't. We have like 10, and it's clearly larger.
Yes.
10
10 is
is
larger.
clearly larger than because it's like 2 letters
Yes.
in these numerals as well.
Yep.
But we have like 6, which is also clearly
Yes, it's
larger.
clearly not as large as 4.
Yeah,
Or sorry, larger than 4. Yep.
yeah.
So
Okay.
yeah, we have lists. We haven't done much with them yet. We have taken
Right.
the length and the sum.
Right.
We can make some of the sort of usual list functions like mapping things.
Yes. Sounds great.
So we'll do like a map function that takes
A function
Mhm.
and
a list.
It usually does, right?
and well, we want to apply the list to something.
Right. So you need to replace the cons,
So
right?
nil can be replaced with nil, so mapping over an empty list to return the
Right.
empty list.
Sure.
So this should replace the cons. It should take a head and a tail.
Mhm.
Tail is the already mapped list.
Right.
So we want to cons the head onto the tail,
But we'll apply the function f to the head.
Right. Yes.
and we'll make like a useful function to test this with. And x, cons x, nil. So
Oh.
make useful.
Now it says ni.
Probably better. And we get.
This is useful
Yes.
because now we have A list of 2 foos?
So now we can map something useful.
Oh, we have a list already, right?
List.
Right, yes.
And get this thing. And
right, and now you had a list with just the foo and the
it's
bar.
not a
and the
list of
box.
lists.
Right, great.
So it has a list of 2 foos in it, a list of 2 bars in it, and a list of 2 quarks in it.
Right. Do you think you could sort of flatten it? Because lists of lists is hard to think about.
so, okay, so
Flattening is easy if you sort of replace all the concepts with append. So
Right,
an append
sure,
function
yes.
that adds 2 lists together.
Do we have append?
nah.
No.
So append takes 2 lists. And
Well, so we already kind of covered this, that lists are kind of like numbers if you only care about the length.
Right, yes.
So append is kind of like plus, since the length should be
Right, so you're going to
the
use the
same
same
as the
trick,
first
right?
list's length plus the second one's.
Right. So you're going to replace the nil in the first list with the second list.
Yeah.
basically. Yeah. Mhm.
so append a list.
Right. And now, yeah, it's
You get foo bar quarks, foo bar quarks.
excellent.
So we can make a flat function.
Right.
Takes a list. It replaces all the cons with append, so it appends
Right.
Each inner list to the next one.
Right.
And the empty list should be the empty list.
Right.
So
You could-
flat, map, useful, a list should get us.
Great.
The list from earlier, but flattened.
Right.
This is clearly like a function that we should give a useful name.
Yes. Do you have any suggestions?
Sort of the flat and then map function. And
Yes.
So we'll make like a function out of it. It takes
Yes.
a function and a list, and it flats and maps.
Right.
I think sort of the obvious thing to call it is greater than equals.
Yes.
Which kind of follows from the definition, I think.
Right. So now you have the fancy hair operator for
Yeah.
the smiley face.
Yeah.
Yes.
And that, so we should be able to map.
So should be able to greater than and greater equal something useful onto
the list from earlier.
Right.
and it computes.
Oh, it's the same
And
thing
get
we
that
had
list
before.
again.
Yes. But now we have the useful operator.
Yeah. I think that's about it. And that's about it. We could do like filter or something over the last 5 minutes, or we could sort of answer questions really badly.
Yes. Should we try filter? Oh, 3 minutes?
3 minutes.
Oh, okay.
Okay.
Maybe we're just done then.
Yeah, so we need booleans to make filter, I guess. And
Okay. No. Oh.
yeah,
Let's
I
not
think
do
we'll
it.
stop for questions.
Yep.
We got like bind in there. So.
Right. So, any questions I can pass on to Jonas?
Is this tool online so I can play with it? Not online, it's on GitHub or
So
You should repeat the question. Is this tool available online, like on GitHub or something?
So this tool is available in my Dropbox, I guess. Do I have like
So earlier we used the Sublime plugin. It doesn't do the equals with hats on them, so we ditched it.
Yeah.
And now I'm stuck in Emacs, which I have no idea how to use. So we can upload we have like this is a standard ML implementation of a Lambda Calculus interpreter. We have a Sublime plugin, which is probably easier to install. It's somewhere on the github.com drawer. It seems like I have internet, but I think Chrome always caches this site for me.
Yes.
But,
so you should check out Jonas's GitHub, basically.
so there's a Sublime, Sublambda something plugin project there.
No.
Yeah. This is like the only sad face so far, so that's good.
Yep.
Yeah.
Yes.
Is it used in production?
Is this used in production?
Yes.
Yes.
It's been used in Haskell for 25 years.
They're using it in the Omniverse.
Yes. Lots of other universes, it's heavily used.
Can we have a copy of your Emacs configuration?
Yeah, so I can't put up the entire. I have it like kind of standalone now, so it's an Emacs setup with only this. I can upload it somewhere and post it. Yeah.
What about the thing that inserts the capybara?
Yeah, that comes with it. Yeah. It's sort of including those two things, the kind of PowerPoint slideshow thing and Lambda Calculus.
And it's also useful for the
two
error
things
message.
you're going to need in the Omniverse.
Yes.
Yeah.
Are we done? Yes.
Yeah.
Thank you very much.